All right, it's a pleasure to introduce our first keynote speaker. Our keynote speaker for this morning is Erik Demaine. Erik is professor at MIT. In fact, I believe he's been professor there since he was 19 years old. Erik's work is largely in algorithms, spanning subjects from improving data structures for web search, studying the geometry of protein folding, and studying the computational difficulty of solving games. He's written a book on the computational difficulty of games, another one on geometry of protein folding. He's also won the MacArthur Award, also known as the Genius Award. Please join me in welcoming Erik.
Thanks. Thanks, it's a pleasure to be here. I'm a theoretical computer scientist, but I also love science fiction. How many people here read science fiction? Yeah, a bunch of geeks. Excellent. And I think we can get a lot of inspiration from science fiction in trying to make them science. I mean, that's why you guys got into robotics, right? So I want to talk today about a few different areas, replicators, transformers, and robot swarms, all motivated by science fiction that is gradually becoming science and has led to lots of interesting scientific problems. And I encourage you to do the same. These are just going to be a few examples, but I think this is a principle we can use a lot. I know these are not robots, these are bullets, but we're going to study a model of robot swarms that is something like bullets you control magnetically. So that's where we're going. But I want to start with transformers, more than meets the eye. I grew up with Transformer cartoons. We have here the Autobots, which according to the lore were invented in 9 million BC. We just haven't discovered them yet. They're among us. And meanwhile, we have Judgment Day of T1000. Around 2029 is when they're created. And here we have one of the cooler robots, the T1000 in Terminator 2, which is made of liquid metal and can arbitrarily transform, whereas the regular transformers only have sort of two configurations. They go between a car and a humanoid. So these are two kinds of goals for transformers we might want to build. You guys have probably seen lots of modular robots. So this is sort of the science side of building transformers. Some of the original designs, there are more than just these three, but I want to focus on these three because these ones we really understand algorithmically. Crystalline robots on the top by Daniela Rus. Can expand and contract 50% in each of here two directions. In general, you could imagine in 3D. You have the M-tran with two modules, a black and a white module hinged together, and they can attach and detach. These can also detach and attach and detach. And here the Molecubes are cube robots that are bisected along a hexagonal bisector and can rotate around. So if you model these geometrically, you have this kind of picture. So each module is one of these shapes. Wherever you have two modules against each other, they can hold hands or not, latch or unlatch. And there's some kind of motion. Here it's a translational motion. Here's some kind of rotation around the hinge. And here you're spinning around a plane. And you want to know, given one configuration of n of these modules and another configuration, can you always go from A to B and how quickly? It would be annoying to have to develop algorithms for all of these different models separately. So one paper we had showed that these models are all related to each other in the sense that you can simulate the crystalline motion of expanding and contracting arms using each of these models. So in some sense, this is kind of a lowest common denominator. And conveniently, we have lots of algorithms for this model, and so we can apply those to the other model. We do lose constant factors, but I'm a theoretician, so it's just constant factors, not a big deal. So you can, in practice, you would want to optimize these constants. But here's an example of how to make an expanding and contracting arm by 50% using Molecubes. And if you put these together in a clever way, you can get all 6 arms without any collisions, even with simultaneous expansion and contraction. So that's how you can simulate a crystalline module with a bunch of Molecube modules, constant number and constant scale factor. And similar thing for M-tran. Probably a lot of models do this, but certainly not all reconfigurable robotic models. A lot of the more recent ones are not quite this powerful. And so here's what we know about algorithms for reconfiguration from one shape to another, if they have the same number of modules, of course. and they're both connected. There's two models, the realistic model and the crazy model, which is more fun. If you imagine that each module can only lift a constant number of other modules or move a constant number of other modules, that's the constant strength, then in the worst case, you need n² operations to get from one configuration to another. It's easy to prove, but you can actually achieve that. There is a reconfiguration algorithm. And what's cool is that a lot of these moves can be done in parallel, almost full parallelism. So in linear total time, you can reconfigure from one shape to another. I have a little simulation of one version of this algorithm. We have fancier ones that are more distributed and more in place, but here's a simple one to think about. So here we have a arbitrary polyomino shape, scale factor of 2. And in the very beginning, all of these are crystalline modules. All of the arms are going to expand. So that's the first move. And then we have this operation which we call melt, where all the parts simultaneously fall to the left. And then we can extract one square at a time from the left repeatedly. And in the end, we'll get a linear thing. And once you get a linear thing, you could play one of these motions backwards and turn into anything else. It's not an in-place reconfiguration. We have nicer in-place reconfigurations that don't use a huge linear space. But what's even cooler, so that's very efficient. Even cooler, but less realistic, this is more in the T1000 kind of model. In almost constant time, logarithmic time, you can reconfigure from any shape to any other if each robot is strong enough to lift all the other robots. So big if. And I have a simulation not of that algorithm, but of a different idea or a different example. So it's an open problem whether you can go from any shape to any other in a constant number of moves. I would conjecture maybe you can. And here's one example to show that might be the case. This is a spiral, and the motion you're about to see is that's like 12 moves or something. Works for any size spiral. It can have n rings. And in a constant number of moves, you can collapse this into a monotone polygon and then staircase it a couple more times, and you collapse it to a line. So any spiral to any line in a constant number of moves, which is kind of mind-blowing first time we saw that. And the idea for a logarithmic solution is to kind of zoom out by a factor of 2 repeatedly. And whenever we zoom out, you kind of make the modules that are within that, here, a 2x2 square and then a 4x4 square and so on, into a nice canonical form so that you can, in constant number of moves, expand to the next level. But we don't know whether this is optimal. We also don't know for sure that it works in 3D, although I think it should. There's a lot of cases to think about. Anyway, that's one perspective on transformers, but I'm going to show you a bunch of different ones. Here's a motivation for why attaching and detaching can be slow. I mean, most robots these days in this space use magnetic latching, but magnetic latching is bad if you're slightly off. This is some mechanical latching, which is super slow. It would be nice if we could avoid latching. So can you avoid having to make parts that attach and detach from each other? And the motivation here is transformers. They seem to be a connected robot. Unless they take a lot of damage, then maybe they fall into pieces. It would be really nice if you could have permanent wiring between all the parts. All the robots I showed you in real life, every component has its own battery. You have to charge them all. It's annoying to get. You have to get communications latching also. It would just be nice if we could build one connected robot that hinge around each other and still be able to reconfigure from any shape to any shape. And we can do that. And another more realistic motivation is nature's doing that all the time with proteins. And we can do that with DNA. There's this cool technology called DNA origami, where with one big strand of DNA and a lot of little strands to make it fold like this, you can build arbitrary, here, 2D shapes. That was the original paper in Nature 10 years ago. But these days, make any 3D shape you want of a limited size at extremely small scale, 100 nanometers, automatically. And it's essentially a connected robot, this chain here. Hard to reconfigure between multiple shapes, but in the mathematical and puzzle world, there's this notion of hinge dissections. Here I'm drawing it in 2D, but same thing works in 3D, where you have one polygon, you want to reconfigure it to some other polygon with a chain of connected blocks. These are permanent attachments, and yet you can convert a square into an equilateral triangle. This is a 100 years old idea. And about 8 years ago, we proved that this is always possible. So if you take any collection, finite set of polygons of the same area, there's one chain of blocks that can fold into each of them without collisions. There's a slightly more complicated statement in 3D. The solution is not especially practical, but it was cool to see that it can always be done. On the other hand, we do have practical hinge dissections for pixel shapes and for polyominoes, for shapes made out of unit cubes. There's a simple way. You take any 2D shape, you subdivide it 2 by 2, and hinge it in this particular way around a spanning tree. And the same chain of blocks can fold into any shape made out of n unit squares or n unit cubes. So it's like a universal robot, and it's permanently connected. So it's a lot easier to build. You can also use it to make fun art. This is an alphabet, a font design where we take each of these little pieces, subdivide it into essentially 2 by 2. And there's this one chain of blocks that can fold into every letter of the alphabet. We built it in a 3D sculpture. And then on the more practical side, we built software to design these things and also to explore reconfiguration. Again, we can show that there's a collision-free motion from an open chain into whatever 3D shape you want. We prove that with a sequential folding, which is maybe not the most practical. What we'd love to do is to show you could do simultaneous parallel folding everything, getting into position at once and make the dog much faster. That's more like how proteins fold. But it's easy to get stuck in this method. So still some interesting questions about this is what we can prove, this is what we'd like to do. And then we built robots to do this. This is with MIT's Center for Bits and Atoms. Different people on each of these robots, different scales. Here each unit is 1 centimeter. Here each unit is about several inches. And here each unit is about a meter. So you can imagine making sort of giant reconfigurable robots. Here we have only a dozen or so units, but in general you have 1,000 units. You can reconfigure it into any shape made out of 1,000 unit cubes, essentially. And so that's cool and exciting. I think you could imagine reconfigurable space structures, reusing your material. Ideally, someday I want this gadget. I push a button and it unfolds and refolds into some other shape that I need. But we're not there yet. That's as far as we are in making chain robots. I think next, so this is using one-dimensional chains to fold something. What about two-dimensional sheets? That's the whole world of origami, which is a pretty active area both on the art and the science side. This is a documentary about the field. And on the art side, there's incredible progress on what you can fold from 1 square of paper, no cuts. And every year we see more and more amazing things. Each of these 1 square of paper, no cuts. This one is the paper is white on one side, black on the other. Crazy stuff is possible. And this is all possible thanks to a growing mathematical and algorithmic understanding of how to design paper folding. One of my favorite results is one that we're just finishing this month with Tomohiro Tachi. It's also free software called Origamizer. You give it an arbitrary 3D model. It gives you a crease pattern. You fold the solid lines one way, the dashed lines the other way. It takes about 10 hours, and you get that bunny. Exactly what you asked for. You can do this not just for paper. This is a sheet of steel that's been laser cut with a 0.5 kilowatt laser, which I guess these days is peanuts. I just saw a 4 kilowatt laser yesterday at NASA Ames. This is Tomohiro visiting MIT folding. This also took about 10 hours, and we get a steel bunny. And in general, any material that can hold a crease, you could fold it into any 3D shape you want. So it's a sort of a simpler form of transformers, more like the Autobots, where we have 2 shapes. We have the flat shape, which is maybe good for storage, transportation. You could roll it up, do all sorts of good things for storage. And then we have 1 target shape, which is exactly the 3D thing you asked for. So more like manufacturing than transformers, but still useful. But it's really tedious to fold these things by hand, so we'd really like a robot to fold the material instead of humans to fold it. And the most success in this area has been in making the sheets themselves robotic. So this is shape memory alloy pulling the creases shut with a little bit of electrical current, and then magnets hold it in shape. And here we were, again, inspired by transformers, or really the T1000. Can we make one sheet that could fold into anything, like we did with the 1D chains? And the mathematical version of this is you take a square grid and alternating diagonal creases, and if you activate some subset of these creases, you can get this one universal crease pattern to fold into any shape made out of unit cubes. So this is like the analog of the 1D strip folding, or 1D chain folding. But there's a little bit of loss of efficiency here, because if you make n cubes using an n by n pattern, which is optimal in the worst case, on average, you have n layers at every point, and you're wasting a factor of n of the material. So a kind of hybrid between the 2D and the 3D, which is a new paper, is if you take a strip of material and this hinge pattern, you can fold it into the surface of any set of unit cubes. And here you only have 2 layers at any point. So this is a lot more practical for making into robots, but this has not been built into a robot. If you'd like to, let's do it. You can prove all sorts of nice things. The ideas of the proof is very simple. You just show how to turn this strip in different directions quite efficiently. And you can even do it continuously without collisions. And you can also fold any letter of the alphabet, which is something we like to do. So back to self-folding. These are a bunch of examples of self-folding sheets. This is one sheet that can fold into 2 different shapes, a boat and a paper airplane, which is cool. And then so this is trying to make transforming things, one material that can fold into 2 different shapes. And on the right, we have 2 examples of more just trying to manufacture one shape out of a sheet of material. So more the manufacturing side. And the right 2 are made with pre-stressed polystyrene. So this is shrinky dink. You heat it up and it contracts. It's a single-use actuator. And you get, the bottom, we're making a crane. On the top, we're making a fully operating robot. Walks away. So that video is a little jerky. And so this is the idea of printable robots, where you start with a sheet of material. It's a few layers. And then you drop in 2 motors and 2 batteries. And then the robot folds itself into a fully operational robot in about 5 minutes. And then acts. It walks around, does whatever you want it to do. So this is an exciting, newish way to think about building robots, which we call printable robots. This is a collaboration between MIT, Harvard, and Penn, where you design your 3D robot on a computer. A computer tells you how to make it out of one sheet, maybe multiple layers if you want to embed the electronics and everything into the sheet. But with a $10,000 laser cutter or whatever, you can build all the parts you need, fold them by hand, or get them to self-fold. So for like $10 or $20 of materials, you can make an arbitrary robot in about a couple hours, which is not the usual way we make robots. So it's kind of exciting, rapid prototyping, education. Every kid can make their own custom robot in this way. And there's a bunch of, there's the algorithmic side of how do you actually take a robot and unfold it into a pattern you can make out of a single sheet, which we still are working on. And then there's a question of actuation. How do you get it to self-fold? I showed one approach to self-folding. An approach that has not been explored very much, but I'd like to encourage you to think about, is zipper folding. So these are examples of making polyhedra by a single zipper. And it's an open problem whether all polyhedra can be made by a single zipper. This is what I mean. I think it's pretty intuitive. I won't define it here. And this is the first example of a zipper robot from last year, I think, by a different MIT robotics group, I think in the Media Lab. So it's an automatic zipper, and you can manufacture some shapes. We don't know what shapes you can manufacture, so this is a different way to self-assemble. Yet another way to self-assemble comes out of the Robert Wood's group at Harvard Microrobotics Lab, where you use the idea of a pop-up card to get flat panels into the desired 3D shape, and then you laser cut away the extra form work here that's just used to make the thing. So this is very small, and you can manufacture, in this case, robo-bees. So what's possible here? And this is a whole new world of manufacturing called Popup MEMS, and there's now CAD tools to design in this world. But what about algorithms? And we're also motivated by real-world Popup books. On the algorithmic side, we can say that if you give me any 2D polygon like this angelfish or any 3D orthogonal polyhedron like this building, we can automatically add internal structure that makes the shape into a single degree of freedom mechanism. And then with a single hinge, you can actuate the structure between a flat, compact state and the desired 3D shape. And so in particular for manufacturing, you would imagine building these layers up in the flat state, and then you actuate it open. Because 2D manufacturing is a lot easier than 3D manufacturing. These are all sort of alternatives to 3D printing. And then you just single actuation, and you've got your desired shape. OK, one more topic in the origami world is curved creases. We've played around with this a lot. Here's what it looks like to put curved creases into a piece of paper. And curved creases are kind of magical in the way that they automatically self-fold the material. And you get these really complicated 3D surfaces with relatively simple crease patterns. So this is attractive for practical applications. This is if you fold concentric circles in a piece of paper with a circular hole, which goes back to the Bauhaus in the late 1920s. And here's an example by my friend Kenny Chung, who's at NASA Ames, of self-actuated. This is some early examples of self-folding, where every crease tries to push a little bit in the direction of mountain or valley, and you get that 3D form fully automatically. Now this, I think, is an exciting next direction to go, which we haven't explored much, except from the artistic perspective. We know that you can make really sophisticated and complicated and very strong 3D structures. These are about 12 inches high, but I think we can go much larger. These are, I think, about 18 inches high, just with sort of self-folding curved creases. And so you can imagine automatically making these, whereas currently we're folding them by hand. All right. So that's the end of the transformers part. And then next is robot swarms and then replicators. So here's the science fiction of robot swarms. There's, of course, lots of movies where this happens. We've got Minority Report here, so seek and destroy. We have taking over the entire Earth on the right, and we have Aeon Flux here, underrated but fun movie where you whistle, and then these swarms become spheres, and then they roll towards you. So over here, we're searching for Tom Cruise. Here, we're consuming the entire planet. It's very, swarms have all sorts of practical applications. The idea is you have many robots. You want to somehow control them together. You know about robot swarms. I'm waiting for my favorite part is down here. Eventually, the swarms accumulate into, so here's some reconfiguration problem. You get them to disperse and then explode to break you out of prison. Very useful. Have to have some positive application of swarms. Here's some science of robot swarms. I'm sure you guys have seen many, but this is the one I've worked with. This guy, James McClurkin, was a PhD student at MIT back in the mid-2000s. And so these are little robots. They're built at iRobot, according to James's design. And they're kind of like they're designed to be a theoretician's dream, essentially. And maybe I'll rerun these movies. So here they're just trying to disperse and fill a space. Here they're trying to find each other, flowing through an environment. The radios here have been custom designed, lots of tricky antenna work to get them to follow the unit disk model. So the true robots can talk to each other if and only if they're within a certain unit distance of each other. I think it's about ½ a meter or so. It's intended to be small so that in a reasonable amount of space we can run experiments that model a much larger space. And so we looked at this problem of how do you detect just the boundary of what these robots can see, given that you only have local communication. And so if you wanted to fill a space, you want to move these guys in towards these holes and these guys out. Oops, That's a black screen. And so we have this model of each robot can talk to any robots within unit distance from them. They can also measure the distance here with some accuracy. And they can also measure the angles between your neighboring robots. That's the model. So you have a complete local geometry, but only local to yourself. Every robot has this. In global geometry, there's this notion of the shape that you're forming, which is if you draw the graph of all the robots that can talk to each other and you fill in all the triangles yellow, then that's the shape, and you want to find the robots that are sort of near the boundary of that shape. And this is tricky, especially for reflex corners. And we don't know exactly how to do this, but I'll show you one thing that's easy locally to do is if you can, just looking at your neighboring robots, if you can draw a cycle around them, and you know that because you know locally where these guys are relative to you, you can measure, you can estimate whether they should be able to talk to each other. And if they can all talk to each other and form a cycle around you in the graph, you know you are not on the boundary of the shape. But that's about all you know. And if you can't draw a cycle, you don't know whether you're on the boundary. But you might guess that you're on the boundary. And so most of the time, this is a correct detector of whether you're on the boundary. But these are some counterexamples of this guy thinks he's on the boundary because he can't draw a cycle all the way around himself. But he's not, obviously. And he can tell that he's not because he's next to a robot that can prove that it's not on the boundary. So out here, the robots that think they're on the boundary form a cycle, and so that's a legitimate boundary. Here, this guy, in one extra round of communication, can discover it's definitely not on the boundary because this guy knows he's definitely not on the boundary and they're neighbors, with this guy thinking he's also on the boundary. You can make some pretty complicated counterexamples, but what we think is true is that if everyone's not moving, and you propagate this information of, oh, I'm definitely not on the boundary, and then everyone next to you concludes that as well, that this converges to the right answer. But we don't know how to prove this. If you want to play with a fun geometry problem, let's try it. Anyway, we built it and ran it on real robots. These are the physical robots, and this is the corresponding real positions. And it works pretty well, especially when the robots are not moving. When the x-axis here is how fast the robots move compared to how fast they communicate. And when that's really small, like a factor of 100, then it's reasonably accurate. Still, this could be a lot better. But as the robots are moving, you don't have time to do this propagation, so things get worse. And if you want to play with these robots, they're at the Museum of Mathematics in New York. And so you can step on them, basically, and tell them they'll follow you around and do all sorts of fun swarm algorithms based on this work. OK, the rest of the swarms part I wanted to talk about is a more recent model we've been exploring, motivated also by this fun puzzle game where you can tilt the entire board and all of the circular objects go maximally in that direction. And in this case, the goal is to get the green guy in the center. So you can tilt to the right, tilt down, tilt left, tilt up, tilt right, tilt down, tilt left, and tilt up. And you get the desired configuration. You've got some things that don't move. And this is a kind of interesting alternate model of really dumb robots. These don't have to be robots at all. They could be particles of iron, and you turn on some magnets, and they move towards those magnets until they hit something that cannot move. And can you get a bunch of objects to reconfigure where you want? This has biological applications. You want to kill cancer. You've got some drugs you want to deliver. You imagine a whole bunch of magnets around your environment. You've got some cellular network that they can traverse, and they won't go through these walls. And here are your initial particles, and you want to have this kind of global control where all of the particles move maximally in a given direction and get each of the particles to where the different parts of the cancer are, and then you trigger them and they kill the cancer. That is a real health application. I'd like to be able to solve it. Unfortunately, this problem is difficult. If I give you an environment and I want to know, can I get these particles into this target spot, that's NP hard. So that's bad news. On the plus side, if you get to design your environment, you can actually build a computer, which is kind of cool, out of particles that you move around in this, very hands-off way. You have global control. You say all particles move east until collision, and then all particles move south. You can build digital circuits out of that. And we actually built them. This is not exactly a robot, but we machined this board, and then you push the board, and you get global control. And here they're computing essentially a NOT gate. And a little more fun is you can design, you can reconfigure particles into arbitrary configurations. So here we have some red and blue particles forming the letter A. We've designed this environment so that if you go north, east, south, and west, you get the letter B. And if you do it again, you get back to the letter A, and so on. Or I think we have a more complicated example. This one, if you go clockwise, you go from A to B. If you go counterclockwise, then you get to C. If you go counterclockwise again, you get back to B. It's a pretty weird. And then you go clockwise, you go from B to A. It's a strange setup. And we built this one too. So here's an A, a little bit simpler. And you can see there's some practical challenges. You don't always go maximally in a given direction. Sometimes you have friction. You can do it. So the theorem is you can arrange these obstacles to arbitrarily permute your robots. Here we just have two types of robots, but of course you could imagine something more general. So this is cool because these are not robots in the traditional sense. These are more like bullets in Neo, right? And he's just remote controlling these bullets without even being able to individually address them. In general, if you have k different shapes you want to make, you can spend a whole bunch of obstacles to very quickly reconfigure from one shape to another. Or at the other extreme, you can make one universal set of obstacles that let you go from any permutation to any other, but very slowly, essentially a bubble sort. And in general, this is hard. But that's what I wanted to say about robot swarms. And the last little bit, talk about replicators. So this is, in a similar world, I want to think about very nanoscale objects. And I would like to build the replicator from Star Trek. I think it started in Next Generation. So it's from about 2400 AD, according to the sci-fi. So we've got a little ways to go. But I think we can build these. And this is in the world of self-assembly, so closely related to a lot of things we've talked about. This is the cartoon version of self-assembly from Howtoons, which I think is just starting to work on some new books. This is for kids to learn about science, build things. This is something you can actually do with, what do they call them? The chocolate-coated O's, Cheerios, essentially. So so sugar-coated chocolate Cheerios, and if you take two that are sugar-coated, they will attract to each other. If you take two that are not sugar-coated, they'll attract to each other, but the sugar will repel from the not sugar-coated, essentially because they are one's higher than the other. The way that they rest is a little different. And so if you do crazy things like dip just corners in the milk to remove part of the sugar coating, you can get them to self-assemble into cool lattices. And if you're really good, you can manufacture arbitrary 3D shapes. So that's the sci-fi. Here is the science with using DNA as our substrate. There's a lot of different ways you could build these. But if you want to go really nanoscale, like 20 nanometer, you can take some strands of DNA that match up in this particular pattern, but have non-matching ends here, so that when you have two of these little units, they will attach to each other and form a big lattice. And so we can think of these as geometrically as squares with these kind of glues at the ends. And so we can make each of these glues different, so that these squares will only attach to squares that have matching glue types. And so one thing you can build is a lattice. This is when all the edges match each other. But you can build arbitrary computers. And people are actually doing this. This is already 7 years ago, building a binary counter in DNA. So basically, there's some seed tile here that's built using DNA origami that I told you about before. And then there's a constant number of tiles that are implementing the computer. They give rules about how to increment a counter. We start with 0, 0, 0, 0, 0. We then get 1, 0, 0, 0, 1, 1, 1, 0, 0, 1, 1, 0, 1. So this is in reverse order. 0, 1, 1. And then there's a manufacturing error. So real life is quite messy at the nanometer scale. And we don't have great answers to error correction yet. But that's coming. A lot of people are working on this model. And the point is you can build real computational devices at the DNA level. Now, this is not a fast way to build a computer. But what's exciting about it is we can compute at the same time that we are manufacturing a three-dimensional object at nanometer resolution. So this is a different way to think about something like 3D printing and replicators. So let me tell you a mathematical model of how this works. You have square tiles. Each of the edges of the tiles have a color. This is a glue. And matching glues will join. So maybe we start out with a tile like this. We imagine there's infinitely many copies of this shape, typically, because infinity is a good approximation for billion or however much you pour into the soup. These are easy to mass produce using biology to mass produce DNA things for us. So maybe now we mix in these two tiles and we see, OK, this blue will match up with this blue, and this green will match up with this green. In this model, you're not allowed to rotate tiles. That may seem weird, but it's easy to implement. And so you don't get this tile gluing to itself. You just get this L shape, infinitely many copies of that L shape. Then maybe you wash away the extra tiles, and you add in some new tiles. This builds a bigger L shape, and those are all the glues that are possible with that rotation. And now I'm going to add a new tile, and I didn't mention one detail. So all the glues I've used so far have strength 2, and I'm in a temperature 2 system, so just one attachment is enough for things to stick. But there are these other glues, the white and the pink glues, that only have strength 1, and so you need 2 simultaneous attachments to be strong enough to attach. So this tile here is not strong enough to just attach here, but it is strong enough to attach in this corner because it's got 2 glues, and 1 + 1 = 2, my favorite equation. So after you assemble here, then the tile will nestle in here, and the tile will nestle in here in some unknown order, and then eventually there, and you'll fill in the square given just the L shape. And this requirement of having 2 glues matching at the same time is what lets you build computers, essentially. But in particular here, I can build a square using just 6 different tile types. This is nice because it's hard to make lots of different DNA strands that are all mutually not attaching to each other. So we'd like to only have a constant number of different glues. And here we can build an n by n square using n stages. In each stage, you build a slightly larger L, and then you fill it in with a square. But that's not very efficient. In fact, if you're more clever, you can still get a constant number of tile types and build an n by n square in log n pores, essentially, of adding this type of DNA tile, removing the excess, adding another DNA tile, and then removing the excess. This is called the jigsaw method. And we have lots of different strategies. This is the original paper in this world of manufacturing arbitrary, here, 2D shapes. But we have a new paper which is much better balanced, so I'll just talk about this one. With a constant number of different glue types and polylogarithmic time, like pore operations, we can build an arbitrary shape with or without holes with constant scale factor. And the constants here are pretty small. So you take your arbitrary polyomino, you scale by like a factor of 3 or so, and then we can build that using a fairly small number of pores. You get full connectivity, so you get full strength. And this works in 2D. In 3D, we have an issue with collisions, which we don't know how to deal with. But hopefully in the future, we'll be able to build arbitrary polycube shapes with nanoscale resolution and sort of automatic through self-assembly. This is basically the replicator from Star Trek, but at least in terms of shape. In fact, in the original Star Trek, you could build food, but not arbitrary objects. I don't know why. Food seems a lot harder to make it all biocompatible, but anyway, and tasty. But there's another interpretation of the idea of replication, which is kind of even cooler. What if I want a shape photocopier? So I take an arbitrary 3D object, I dip it into a vat, and then I pour in some DNA tiles. I would like those tiles to measure the shape and then print copies of the shape. And a useful application of that, if you want to take over the world, is you have some future technology that's been time traveled back to you. You don't know how it works. You don't even know what the shape is fully. You would like to measure that shape and mass produce those shapes. But 3D photocopier. And we can build that in this model if we add one extra construct. What I've shown you so far only lets things grow. You can never shrink. So we need some way to be able to detach components if we want to sense and then replicate. And so here's a model. There's a couple different ways to do this. If you add another type of tile called RNA, or made of RNA instead of DNA, and then we have an RNAse enzyme, which basically just eats all RNA, destroys them, then you can build some shape and then separate it into two parts. And then maybe add some more tiles and do other cool things. So this is a model from 6 years ago. And now we can build replicators without even knowing what the shapes are, which is cool. So suppose we're given a rectangle. We don't know its dimensions, but just a rectangle for now. We can build a little L shape, build one for each corner, and have them glue to those corners. And we've now detected the corners without knowing where they are. Then we can add some sidewalls. All of this is built out of RNA. Do the same thing with DNA, and then add the enzyme. And we've now built a mold of our shape without knowing what it is. And then we can do the reverse process and fill the mold. And now we have, and apply the enzyme. We've now doubled the number of copies of the shape in a constant number of rounds. And in log k rounds, we can make k copies. So like in your photocopier, you hit 100. And you can run this strategy and get exactly 100 copies of your shape in log 100 time. Even cooler is with a constant number of tiles, one stage, one use of the enzyme, you can, given a single copy of the rectangle, build infinitely many copies of the rectangle. Or in other words, as you feed this machine more and more, it will produce more and more copies. It's a little harder to control, but it's less work. You only have to make a constant number of tiles, pour them in, and you're done. And it's essentially copying this length to this length to this length, and so on. And then these lengths are easy to copy. All of this is made out of RNA. You apply the enzyme, and you get all these copies of the shape. That's for rectangles, but we want arbitrary shapes. So this is for 2D polygons without holes. You can detect the upper left corner and build a binary counter, like I showed you before, to build walls around the sides of the shape, build a mold, essentially. But then wherever there's a black line here, make it out of RNA. So when I apply the enzyme, these parts separate. Now I have rectangles. I know how to replicate rectangles. I can make infinitely many copies of these rectangles in constant time in this model. And then add some more stuff back to these corners. I built the binary counter so that each of these rectangles knows the label of the adjacent guy. And so they uniquely assemble back together just like a T1000 Terminator 2. And you can then, now I have infinitely many copies of the mold. I fill the mold, and I get the shape. There's a lot of details here. It's quite complicated. We have not built this in practice. It's probably beyond what we could do. But we built a simulator to make sure it all works, because there's a lot of details you can easily get wrong. Here's just one case of the algorithm, which is challenging. The yellow here is the original shape. And we're building this binary counter. Here it says 1010 down the sidewall. And it's constantly copying the values up to the north side here, because when we collide with the shape, we have sort of no time to copy the value that's here onto the value that's here. So we're constantly copying it up so that when we hit a wall, then we can detect in this corner that something bad happened. And then we go to the left to read the string back and copy that string back up here. And at the same time, we would increment the counter here and then continue up. So it's kind of crazy, but it's a very fun model of computation if you've never seen self-assembly. This is basically the computer is geometric. You're physically moving an environment as you're computing stuff, and you only have a constant number of bits of information locally. So it's I don't know, it's kind of like robotics, but a little more hard, because each unit is very simple. Fun model to play in. So in general, if we want to make n copies of a shape, we can do it in log k stages, infinitely many copies, constant number of stages. Currently, we need no holes, and this is only in 2D. We have ideas on how to extend it to 3D, but it's always challenging. Someday we'll build this. For fun, you can also, as you're replicating, magnify your shape to make it larger or smaller. This could be useful if you have a very fine shape like a protein. It's so small we can't look at it. You could imagine building one of these molds and in the DNA system, scale it up by a factor of 100 so that then we could look at it with an electron force microscope, whereas currently we can't. So magnification would be a nice way to actually look at very small things. And miniaturization has other practical applications. And we have a brand new paper in upcoming SOTA about another way to build shape replication where instead of this enzyme, and enzymes are apparently very messy to work with in practice, we have a negative glue. So we have DNA that repels each other. This is apparently possible. And if you have negative glues, you can also build replicators. It's even harder than before, but it can be done, and you can check that out on arXiv. And I think that's it for my sampling of building replicators, transformers, and robot swarms. These are, of course, not the only models for how to do this. I'd encourage you to try more, but I think science fiction is really a fun way to inspire lots of cool science and geometry. So thanks.
Questions?
Yeah.
Where you have more like a Rubik's Cube rotation as well. Did you ever look at modeling those? That make the transformer thing a lot easier, it feels like.
Right, it could, yeah, so we were looking at chain robots in this very simple kind of hinging, mostly because it's easy to think about. I think many models should suffice for getting universality, and here we didn't worry too much about transformation time because we still don't have a good handle on that. Maybe by doing Rubik's Cube style simultaneous reconfiguration of many parts, you could do better. Rubik's Cubes, though, do not stay permanently connected, of course, because the parts are permuting. Or do you just mean the twist hinge versus a rotation hinge?
Yeah, I just mean, yes.
That shouldn't make too big a difference. I think you could build it either way and get the same result, but we need to double check. Yeah.
Do you need? Is it possible to characterize the space?
Yeah, so how much space do we need in order to arbitrarily reconfigure a bunch of pebbles with tilt? We have two results at an extreme, but I think that in general there should be a kind of time-space trade-off. So on the one hand, we can show that if you have a very small amount of space, essentially linear space in the number of modules, then you can, that's enough to reconfigure between any permutation, but the time it takes to do that is quadratic. So it's very slow reconfiguration. I would guess maybe n log n time should be possible with linear space, but I'm not sure. It's sort of like sorting algorithms or sorting networks. And at the other extreme, we know that if you have lots of space, linear in the number of different configurations you want to build, which in general could be exponential, then you can very quickly reconfigure from one shape to another, in like logarithmic time. But in between, there should be some time-space trade-off, which we haven't fully characterized. But yeah, so still nice questions there.
Curious about the role of randomness in these algorithms, and some of them it's sort of in the background. To what extent are you actively trying to? To what extent are you trying to actively exploit randomness?
I would say so far we're not exploiting randomness at all, and maybe that's to a fault. And you see it especially in the self-assembly world where randomness is just the name of the game. And all of our algorithms are designed to be deterministic. And if there's any random failures, then everything falls apart. Ideally, we would embrace randomness more and actually be able to exploit it to do things faster. But so far, we're not doing that. So I think that's a good direction to go, but not yet. Yeah.
Erik, I just want to follow up on the statement that it's first of all, I love the work is fantastic, and
Thanks.
it's a great talk. Perfect for wafer, by the way.
It's my first time.
Yes,
thanks for
but
having me.
you fit in perfectly. What I was curious about the statement that it works for an arbitrary three-dimensional shape. So
For which result? Or
the folding, the original original section and transformers you talked
Yep.
about, and I'm just curious, are there any limitations? I mean, it seems like something on curvature or something with holes, or there's some aspect that would not be could not be foldable.
so we're talking about which foldings?
It was from a flat sheet, I think.
Oh, okay, yeah. So from a square with this grid pattern, we can make arbitrary shapes made out of cubes. So the catch here is that we're assuming zero thickness material.
Okay.
So I mean, this is how you fold this shape. So it's quite complicated and messy, but you can make the surface of any n cubes. And in fact, we even build the square panels that are not on the surface, also the interior panels, with this folding.
Okay, so but then going back to the bunny example, where you have
Okay, so bunny does not fall into this because it's not made out of unit cubes. Of course, you could approximate this shape with unit cubes. I see. So you're asking about this one. Yeah,
that's
okay.
the
Yeah. So this is not yet finished. We've been working on it for a long time, almost 10 years. But we just submitted it. I think we will soon release to archive a proof that you can make any 3D surface. I mean, there's a topological limitation.
Yeah.
If you don't allow gluing of material, then the best you can make is a topological disk. But if you, in this case, we're making a sphere by cutting it. You can take any topology and cut it until you get a disk, essentially. And then you can fold from a square paper that topological disk.
Okay. All right. We have a topologist here who can.
Yeah, so this is exciting, but it's complicated. We don't have a theoretical sense in which this is good, except we could say it's watertight. So, but we don't have a bound on how efficient it is. In practice, it seems really efficient. Like here, we're using, I think, about a quarter of the materials being used for the surface area of the thing. And a quarter is about what practical origami achieves too. Most of these examples are also about a quarter, but we don't know how to prove that. It's probably not true in general. It'd be nice to characterize what shapes can be made with a constant scale factor. There's a question over here, yeah.
Is there a way for you to take as input the structural properties of the end product and use that to then design a variety of methods to fold desired properties?
Yeah, good question, especially for this audience. I basically only focused on geometry here and not mechanical properties. And short answer is I don't know how to do mechanical properties. I hope it should be possible. And we've been running into it with the printable robots in particular. I think there are good answers to that, but I don't have them, I'm afraid. That's future work also. And here.
So you guys just probably read it. Does the design just handle the initial and the final geometry, or does it have a collision-free continuous trajectory?
Okay, good question. Is there a collision-free motion from here to here? Obviously, in practice, there is. We can prove, in general, for any origami made out of a topological disk, there is a continuous motion without collisions. It's a terrible motion. And so in particular, you'd really like to know whether this can be folded into that rigidly, with each of these panels remaining a flat polygon. So you can make it out of steel, like we did. That we don't know. That's not always true. For these designs, it might be true, but we don't know how to prove it. In general, the computational origami world is really good at final designs, and there is a general theorem that says it is possible if you contort your paper. You don't have to stretch the paper, but you might have to add lots of creases to do it. We're not very good at giving nice motions, but that's an active area of research, rigid origami, and slowly making progress. Here we don't know that.
All right.
Cool.
If there are no more questions, let's thank Erik again.
Thanks.